Hey, good evening, everyone. Welcome to this lecture. So this is the last lecture in this public lecture series. And it's a series of lectures that is named after Heinz Pagels, who was a professor at Rockefeller University, who tragically passed away in a mountaineering accident just near Aspen. And he was advocating for the effective communication of science to the general public, himself writing a couple of popular science books. And so the Center of the Aspen Center for Physics is now honoring his name and work through this public lecture series. Okay, so although this is the last lecture of the season, I would like to invite you to join the mailing list for this public lecture series for the next season. So you can do that by signing up on the sheet in the foyer or by contacting the Aspen Center for Physics either by email or phone. So this public lecture series is brought to you by the Aspen Center for Physics, which in its 60-year existence has been a place of great importance in the world of theoretical physics, bringing together researchers from all over the world to think and discuss and collaborate on some of the most fundamental questions in nature. So it's a center that the center is a non-profit institution, but it's partially funded by the National Science Foundation as an investment in the nation's scientific base. Okay, and then before introducing the speaker, I would like to request in the name of the center that all participants in this event and all of the Aspen Center for Physics events conduct themselves in a manner that is welcoming to all other participants, treating each other with respect and consideration, free from any form of discrimination or harassment. Creating a supportive environment to enable scientific discourse is central to the mission of the Aspen Center. So then now it is my great pleasure to introduce you to Douglas Stanford. He obtained his Ph.D. at Stanford University in 2014. He then spent several years at the Institute for Advanced Studies in Princeton before returning to Stanford, where he is currently an associate professor. He is the recipient of several prizes, including the Vivotnik Award for Young Scientists, the Breakthrough New Horizons Prize, and the Griebel Medal of the European Physical Society. So these illustrate the importance of Douglas's contributions to physics, focused on black hole physics, chaos theory, and the holographic approach to quantum gravity. We're very happy that today he will tell us about black holes and quantum teleportation.
Okay, great. Thanks very much for the kind introduction, and it's a pleasure for me to be here. One request I would like to make of you guys is that you feel free to interrupt me and ask questions during the talk. It is more fun for me, and I think probably more fun for folks as well. Okay, so let's start with Einstein. So Einstein made many very important contributions to physics, the different areas of physics, but there was one particular thing that he's very famous for, one equation that he's associated to, which is kind of more important than any of the others. I'm not sure if you guys know about this equation. This one? Not that one. This is the equation that is so important that it's referred to as Einstein's equation, not the other one. And what this equation says is it says that matter makes space-time curve. So this is the equation that describes the theory of general relativity. So you can try to make a picture of that, probably a picture that you've seen before. Here's what it means that matter makes space-time curve. So let's first start out with a case with no matter. Well, this is a picture of flat space and a couple of rocket ships moving around. And if we add some matter, you can see the space-time curve somewhat, and the rocket ships can feel the influence of the matter through the curvature of space, or more generally of space-time. If you add more matter, more suns, then the space-time is more curved. Rocket ships feel the gravitational force more. And if you imagine adding more and more matter in any given place in space, eventually the space-time will become sufficiently curved that there's a horizon that forms. And what the meaning of a horizon is it's a point beyond which no signal can get out. So the horizon is supposed to be represented by this black line here. And the idea is that nothing can exit this region here. Here, you might get sucked into the black hole, but if you have a sufficiently powerful rocket, you'll be able to stay away. But once you cross the horizon, then no matter how powerful the rocket is, you won't be able to leave the black hole. So that's a kind of a strong version of the idea that matter makes space-time curve. Okay, so here's a better picture of the same thing. We have this rocket. It's out here in the region where space, or more accurately space-time, is fairly weakly curved, but it becomes more strongly curved. And you can imagine that this line here is the horizon. Anything that passes beyond that point is doomed to fall into the black hole and will not be able to make it back out. Okay, so what does a black hole look like in real life, as opposed to these sort of fanciful drawings of curved space or curved space-time? So here's a somewhat fanciful picture of a black hole, and you can see this sort of distortion of the light from behind it, and that's a consequence of the curvature of the space-time between us and the stuff that emitted this light behind the black hole. But the last 5 years have been an exciting time for people who work on black holes, because now we have more data, more real data about actual black holes. This here is a picture from the Event Horizon Telescope of an actual black hole. So it's not an amazing picture, but it's amazing in that it's a actual picture of a black hole. You can kind of see the dark region in the middle that corresponds to the actual black hole. Okay. So that picture was from a couple of years ago, but about 5 years ago, there was something even more exciting from perspective of many people who work on black holes, which is that there was a detection of gravitational waves from a pair of colliding black holes. This was the LIGO experiment, an experiment which detects gravitational waves, and they detected gravitational waves being emitted by a pair of black holes. So you can think of those as a couple of these objects, curved space-time objects. Each of them has a horizon. And you can imagine that if they get close to each other, they can attract each other. And generally, there'll be a little bit of angular momentum, so they won't just fall straight into each other. They'll kind of orbit around each other to some extent. And then eventually, they will form one black hole, one horizon, a larger horizon, together with ripples in the space-time that emanate out from that point. Think about throwing a rock into a pond or something like that. There will be some ripples that propagate out. The LIGO detector actually measured these ripples in space-time. So this is an incredible process, and I want to show you a simulation from the LIGO experiment. This is a simulation of what that might look like. These two black holes that we start with are kind of orbiting around each other, gradually getting closer. And the process kind of speeds up as we get closer to merging. Then finally, the two horizons merge into one horizon, end up with one black hole and a little bit of radiation going on, flying away from this merger of the two black holes. Okay, so let's go back to this. This is a kind of a picture of the space-time after the merger. Have a new horizon which formed from the two original horizons of the two separate black holes, and some ripples emanating out. Now, this is an absolutely incredible process. which kind of boggles the mind in terms of scales of matter and energy. So to kind of illustrate this, let's do the following calculation together using that other Einstein equation, E equals mc squared. So by studying the detailed pattern of the gravitational waves, the LIGO team was able to estimate the masses of the two black holes that collided, also the mass of the final composite black hole. So what they believe is that the first black hole was about 36 times as massive as the sun. And the second black hole was a little bit smaller, but still quite big. It was 29 times the mass of the sun. And okay, so if we add those up, what do we get? 36 plus 29 is 65. So the initial amount of matter in these two separate black holes was 65 times the mass of the sun. The final black hole had 62 solar masses. So the mass of the final black hole was 62 times the mass of the sun. You'll notice that there's a difference there between 65 and 62. There's 3 solar masses that have gone missing. 3 solar masses have gone missing in this collision. Where did those go? Where did those 3 solar masses go? Oh, they were emitted in energy, exactly. So in energy, they were emitted in the gravitational wave, primarily emitted in the gravitational waves, were emitted during the final moments of the merger of these two black holes. As they're rotating around each other, they're emitting gravitational waves for a long time, but the power increases dramatically towards the final moments of the merger. And actually, a lot of the power, a lot of the energy is emitted, a lot of the 3 solar masses was emitted in the last 100th of a second in collision. So here's the calculation that blows my mind. Let's try to calculate how much power is being emitted during the final 100th of a second in this merger of two black holes, collision of two black holes. So power is what? Power is an amount of energy divided by an amount of time. So the amount of energy was emitted. Well, energy is mass c squared. That's E equals mc squared. So what's the amount of energy? It's 3 solar masses times c squared. So this is the mass of the sun, roughly. This is 3. We take this amount of energy, 3 times the mass of the sun times c squared. We divide it by the amount of time during which that energy was emitted. And that's about 100th of a second. Okay, so that's, well, that looks like there's some big numbers getting involved there. That's a good sign. I'm a high energy theoretical physicist. I'm not great with these kinds of calculations, so I put it into Google, and it spits out following answer. This is the amount of power that was being emitted in gravitational waves in watts. Watts are a ridiculous unit to discuss this in. Like, watts are something that makes sense for humans and light bulbs and stuff. But well, numbers work, so we can express it in watts. It's about 10 to the 49 watts of power. So, okay, that's a big number. What does that mean? That's a lot. So let's try to compare it to something. A star like the sun emits about 10 to the 26 watts of power. Look this up. I didn't calculate that. Most mainly invisible light, meaning the stuff that we can see when we look at the sun. The total amount of power that the sun is giving off is around 10 to the 26 watts. Okay, so that's not big enough. We need more. Well, it so happens that there's about 10 to the 22 stars in our observable universe. 10 to the 22 stars in our observable universe. If we take all of the stars, that means stars that we have observed. I mean the number of stars that would be possible for us to observe in our backwards light cone. So the total power emitted by all of the stars in the universe is 10 to the 22 times this. Okay, so what is that? That's 10 to the 22 times 3 times 10 to the 26. That comes out to 10 to the 48. What was the black hole doing? The black hole merger was emitting 10 to the 49 watts. So black hole, these two black holes merging were briefly emitting more power than all of the stars in the universe. So this is it's amazing, right? That is absolutely amazing. So that is the reason why this is Einstein's equation. That process, that incredibly powerful process, boggles our imagination. That is something that we know how to describe calculate using this equation. So that's yeah, please.
Your initial picture of a black hole.
Yeah.
Seems to imply that it has some dimension. What was the mass of that black hole and what was its dimension if that can be measured?
What does dimension mean? Sorry.
Well, just the radius.
Ah, okay, good. So yeah, we can work that out. So the black holes had roughly 30 solar masses worth of mass, and the horizon of a black hole, the radius is proportional to the mass. And so the thing you can remember is that I hope I'm not saying this wrong. I believe that a solar mass black hole have a horizon, the radius that's about 1 kilometer. So these black holes had horizons with radius that's about 30 kilometers. What does the radius of a horizon mean? It means the things such that if you compute the area, the thing is well defined as sort of the area of the horizon. And so this is the radius such that if you computed an area from it, you get the right answer. It's about 30 kilometers. So they're big as far as objects go. They're pretty small to be emitting more power than all of the rest of the universe at that time. Okay, so this is yeah. Another question? No. Okay. All right. So that's Einstein's equation.
The merger itself, the reason they don't just orbit each other forever is because of gravitational radiation, or
well, that would do it. That would do it. It might be that there's also like the black holes are not completely in empty space-time. There's some stuff around them, and that might contribute as well. I don't know. I don't know whether it's that or whether it's the gravitational radiation, but either effect would be enough to cause them to spiral.
So the process of these two black holes going around and then merging, how long does that take?
Well, so it depends what you mean. It's a process that went on for a very, very long time. And for a very, very long time, they were just orbiting each other, looked like nothing much was going on. Looked like they were pretty much in stable configuration, orbiting many, many times. I'm not sure how long, but an extremely long time. And they were slowly losing energy, just a little bit, getting close to each other. And then most of the action, most of the good stuff happens in the very last 100th of a second in this merger.
Millions of years.
I'm sure that they were orbiting for much longer than millions of years beforehand. Like they were orbiting for astrophysical timescales, but most of the power was emitted in the very end.
Yeah. Is the event horizon only on a horizontal scale, or is it at like a ball, all dimensions?
It's like a ball. So it's like a two-dimensional surface. It's like a beach ball kind of thing.
Then would at the poles would the forces be less because of the rotation?
Oh, you mean the rotation of the orbiting objects?
If the black hole is rotating, you got spin, mass, and charge, and on the horizontal plane you have the event horizon, but you're saying it's a ball.
Yeah. So for the case of a rotating black hole, the horizon is a shape that's not exactly a round beach ball. It's somewhat some different shape,
Yes.
which represents what you're saying, but it's a little bit different near the poles than near the equator. But yeah.
So there's an exponential loss of energy then. So it's losing more and more energy as they get closer and closer.
So losing more energy as they get closer and closer, but not very much happens. So the physical scales involved are pretty low until the final merger, and then a really dramatic thing happens. Horizons merge, the space-time is highly curved, and all this gravitational radiation gets emitted. Yeah.
Okay, so as these black holes are merging, they're losing mass at the last 100th of a second, or actually even thousandth of a second, probably have a huge influx of it or outflux of energy.
Right.
In the form of gravitational waves. You have a loss of mass, and so that mass is directly convertible into gravitational waves.
Yes.
Okay, so or some other kind of energy. Although I'm
Mainly gravitational waves.
from what I read before, I was not aware if there was any neutrinos or gamma rays from that event.
But
if there was, it's probably pretty minimal. But at the same time, the gravitational waves are being released. if there's a loss of information from the black hole, from the event horizon, would you be looking at that information also being in a form of actual space itself? And could you then link that in some peculiar way to Hoyle's steady state theory?
Okay. Let me try to answer the first question, which is whether there was also electromagnetic radiation that was emitted during the merger. And of course there will be some, because there's some stuff around the black holes, and that stuff, accretion disks, and that matter will collide to some extent, but it's very minimal compared to gravitational waves. That's different from what happened in another collision that Bill saw, which is they observed a collision of two neutron stars. And neutron stars don't have an event horizon. They have all this matter just sitting there. In the collision, matter smashes, one neutron star smashes into the other neutron star, and you have real matter gliding. That emitted a whole bunch of energy in gamma rays, which was detected in conventional telescopes, in addition to the gravitational waves that were detected with the LIGO device. But for these black holes, there's just not much matter around. Basically, by this point, they're basically just pure space-time objects. The thing that happens in the collision is these space-time shapes merge into one somewhat larger space-time shape. So I didn't completely understand the second question, but maybe you can ask later. I want to move on now. So, okay. The goal of the first part of this talk was to impress you. So this makes black holes sound very impressive. They are very impressive. It's crazy scales involved. But that's actually not why they are important to present-day high-energy theoretical physics research. So the kinds of things that people like me work on, that is not why we work on black holes. It's impressive, but it's, I find it cool, but that doesn't really have anything to do with my research. The reason that we work on black holes is different, and there's a risk that it's going to seem kind of boring. So I'm going to try to convince you that it's amazing, but the rest of the talk is going to be harder to find amazing. Let's put it that way. Okay, so let me try to introduce you to the different types of theoretical physicists. I'm not going to get all of them, but I'll discuss three categories. So there are condensed matter theorists, and we have some of them at ACP right now. So the basic problem that condensed matter theorists study is the following question: when you take a lot of particles and let them interact, matter, and let it interact in different ways, in particular, in a regime where quantum mechanics is important, what happens? What kind of phenomena can be exhibited by those interacting particles? And an example of the kind of surprising and important phenomena that you can uncover is superconductivity. This is roughly speaking what condensed matter theorists do. I hope the condensed matter theorists who are in the audience will not take offense from this description. Okay, so there's another class of theoretical physicists, general relativists and cosmologists. Basically, what these people study is Einstein's equation. Study Einstein's equation and look at different kinds of solutions, like describing black holes, describing collisions of black holes, describing the evolution of the universe itself, which is a dynamical system described by Einstein's equations. So that's the kind of thing that these people study. And then there's a third category. This includes me, high energy theorists. And the thing that we are trying to understand, roughly speaking, is what are the basic rules, that describe physical reality. An example of something that many of us work on or use in our research is string theory. When it's an attempt to give a mathematically consistent set of rules that can describe our physical reality, that would reduce in certain situations to Einstein's equations and to the rules of interaction for particles. These are three different types of theoretical physicists, and all three of these types of theoretical physicists are interested in black holes. And the kind of thing that ties their interest together is the following concept. It's a duality. So, okay, duality in physics, what that means is it's a kind of secret equivalence between two seemingly different systems. So an example of this, not from physics, but just an example of it, would be suppose you have a movie that you could store on a DVD or VHS, And these are different objects. The DVD and the VHS are very different objects. But if you kind of decode them the correct way by putting them into the appropriate player, then the movie is the same. There's something the same about those two objects, but the abstract information that is stored by them, even though the media are very different. And that's a kind of dualities are kind of like that. Dualities in physics are kind of like that. Two rather different physical systems are secretly the same. The most important duality in physics is called the ADS-CFT duality, or ADS-CFT correspondence. And it was discovered by Juan Maldacena, who is actually at Aspen Center for Physics right now. And what is it? It's the following absurd statement. So the statement is that an interacting system of particles, a particular one, or a particular class of interacting systems of particles, is this kind of thing. The condensed matter theorist study. The claim is that a particular example of that is actually secretly describing a higher dimensional gravitational theory. So something that cosmologists or general relativists or maybe high energy theorists would study. So a system without any gravity at all, just some interacting theory of particles, no gravity, interacting particles, is supposed to be dual in this sense, so secretly absolutely equivalent to a completely different looking system. That completely different looking system is a theory of curved space-time in higher dimension. Higher dimension. But that, well, okay, so imagine I tell you this, you say, I must not be understanding what he's saying. It doesn't, I can't like compute this, but that's not, you're understanding what I'm saying. It's just it's an absurd statement. It's an incredible fact that appears to be true. Appears to be true. And so why does this mean that these three different people care about black holes? Well, it means that these interacting systems of particles, in some cases, are really describing a space-time. And important, interesting thing that can happen in a theory of space-time is we're going to have black holes. So there are states of interacting systems of particles that are somewhat related to the types of systems that condensed matter theorists study, that are actually secretly describing a black hole. So if I study a black hole, I can somehow map that calculation, that system, onto some system, completely different looking system of interacting particles. So now the different communities can talk to each other. We can compare our calculations. As matter theorists do some calculation on their interacting system of particles, or they discover some type of qualitative effect. And then somebody studying a black hole can go and try to set up a computation and find the same effect. And it's actually, that's a lot of what happens here at ACP, is they bring in people from different communities, condensed matter theory, relativity, string theory, talk to each other, we compare calculations, and try to better understand this absurd equivalence, this ADS-CFT duality. Okay, so what I'm going to do in the rest of the talk is I'm going to explain one example of that. So the example is going to be a black hole that is implementing a sort of purely quantum mechanics operation. So something that would make sense over here. And I'm going to show you how the black hole does it. All right. Okay, I'm going to try to show you how the black hole does it. So, all right, so the thing that the black hole is going to do is called quantum teleportation. And I'm going to show you some cartoons to illustrate first what ordinary quantum teleportation is before we get to the black hole. So forget about black holes for a minute, think about the cartoons. So before we talk about quantum teleportation, let's talk about something simpler. This one is called communication by shouting. So Alice here has just flipped a coin. She got the result heads. She wants to tell Bob what she got. So she shouts, it's heads. And then Bob says, okay, great. He now knows that it's heads. What if they want to do something a little bit more complicated? Can communicate the same information using something called one-time pad cryptography. The way that works is that Alice and Bob in advance share a code book. Code book has something written in it. It could be heads, could be tails. In this case, it was tails. They have the same code book. So Alice flips her coin, she finds heads. She wants to tell Bob the answer was heads, but she doesn't want to say it explicitly. So what she does is she consults her code book. She discovers, heads is the opposite of tails. So she says, hey, Bob, it's the opposite of what's written in your code book. Bob opens the code book, he says it's tails. He says, okay, I should take the opposite, it's heads. That's one-time pad cryptography. It's actually It's a type of cryptography. Just to make it more explicit, here's what it looks like. Alice takes the result of the coin plus her code book. She spits it into a machine that compares them. It spits out the fact that they are opposite. She says it's the opposite. Bob takes his code book plus the word opposite, sticks it into a machine. Out comes heads. And now Bob knows the answer is head. Okay. Now you're ready to understand quantum teleportation. Quantum teleportation is the goal. Alice has a quantum state, psi. This is the way we write quantum states, letter, and this funny symbol invented by Dirac. So she says, I have a quantum state. I don't know, how am I supposed to say? I can't shout quantum state. In particular, quantum states are hard to transport. In particular, if you don't know what it is. Alice might not know what the quantum state is. She has a physical system, a quantum computer in a particular quantum state. He wants Bob to have that quantum state. He might not know what it is. If she measures it to find out what it is, he might destroy it. And even if she knew what it is, it might be that he cannot communicate it to Bob because quantum state requires a huge amount of classical information to convey. So it looks like Alice is really stuck. It looks like the only way she's going to be able to get Bob to have the quantum state is actually to physically take the system, has the quantum state in it, and hand it to Bob. It doesn't look like there's any way that she can just communicate to him what the quantum state is. Quantum teleportation is a protocol that was invented in the early 90s that solves this problem. And it's kind of similar to one-time pad cryptography in that it makes use of a pair of code books that are shared by Alice and Bob. Instead of just being a code book that says heads, heads, or tails, tails, these are a pair of quantum entangled code books. So entanglement, that means is that the code books have a particular and strong type of correlation that is possible in quantum mechanics. You have probably heard about that, about quantum entanglement in previous ACP talks. For our purposes, what's important is that it's a type of state that these two code books that could be in, where they're very highly correlated with each other. Highly correlated. Okay, and it turns out that although it is impossible for Alice to call Bob up on the phone and tell her the quantum state without the entanglement, if they have these entangled code books, then she can do it. Then she can send the quantum state. It works. It's very similar to one-time pad cryptography. She takes the quantum state together with her copy of the code book, sticks it into a machine. The machine does some measurement, comparison, which is not too different from what we were discussing before. It outputs a number, let's say 3. Alice just shouts to Bob, 3. He takes the number 3 together with his entangled code book, sticks it into a machine, and out comes the quantum state psi. So that's the structure of quantum teleportation. And it's actually, it's an important protocol in quantum computation, quantum information theory. Technically what it does, it allows you to send a quantum state using classical communication, so just saying the number 3 over the phone, plus a resource that you have to share in advance. Resource you have to share in advance are these entangled code books. Okay, so I'm going to now discuss the implementation of quantum teleportation by a black hole. And I'm going to try to do that. This is a bit of an experiment. I'm going to try to do that using the black hole. So yeah, we've gone a long way in terms of impressiveness from black holes that emit more power than the entire rest of the universe, like some Blackboard discussion. But this is actually, in my opinion, this is the good stuff. This is why people like me care about black holes. I want to share that with you guys honestly. Okay. So here's the idea. What we want to do is we want to do quantum teleportation. We want to accomplish it instead of using a pair of entangled code books. We want to accomplish it using a pair of entangled black holes. Quantum teleportation, the entangled code books are something you have to share in advance, and they're a resource that allows you to do the task, allows you to do the quantum teleportation. First question we should ask is, what type of a resource is associated to a pair of entangled black holes? Let's a picture. This is a picture similar to what we had before. Here's our space. I'm going to draw a couple of black holes. So this picture is supposed to represent unentangled.
Unless that black body is difficult to see from here.
Oh, you mean because of the height? Okay, can you see this one? This much at least? No.
Circle's darker.
Ah.
There you go.
Oh, it's not a question of the height. It's just the chalk.
Correct.
Okay, thank you. So this is what unentangled black holes look like. So horizon is somehow here, and the black holes are this kind of curved regions of space. Can you see if I draw here, or should I move to the other? No, okay, I'll move over here. Okay, so this is a picture for entangled black holes. We start out by drawing exactly the same thing. These two holes. Now the picture is that they are connected. Space inside the horizon. So here are the horizons. These are the points of no return. Space inside the horizons, instead of being these two separate regions here, they're connected spatially. That's the difference. That's the geometrical difference between unentangled black holes and entangled black holes. There's a question? That's a wormhole. So this thing is called a wormhole. It's a wormhole that connects these two regions outside the black hole. Entanglement. Makes them connect like that is the entanglement of the two black holes.
How does that happen?
Well, that's not very well understood. It's not very well understood, for example, what the best way is to form a black hole like this, or exactly what it would look like as you're transitioning between a state like this and a state like this. But it is believed with high confidence that if you can prepare a special entangled state of black holes, then regions behind the horizons will be connected by a wormhole. And so that, intuitively, that is the resource. That's the resource that we're supposed to use. The connection between the two black holes. Yeah.
Do you know about any of these, or is this?
No. Good. Thank you for asking that question. So in the first part of the talk, I talked about actual black holes. They are amazing and impressive and great. In this part of the talk, we're not talking about actual physical black holes that exist somewhere and collide and that we can look at with telescopes. What we're thinking about here is the abstract connection between black holes and ordinary quantum mechanical system. And so in an ordinary quantum mechanical system, I can form an entangled state of copies. So then we're led to ask the question, what happens if I form an entangled state of two black holes? I don't need to worry about whether that actually exists somewhere in the universe. I don't need to worry about going and finding a pair of entangled black holes or trying to make a pair of entangled black holes. What we're trying to do is understand this connection between black holes and ordinary quantum systems. So for that, it's not important that they actually physically exist somewhere. So I warned you that I'm taking a risk here and explaining why we actually care about this, but that is true. Yeah, you had your hand up?
Doesn't really answer the question about the information.
No, it does not by itself. There are related wormholes that help answer that question, but I'm not going to be able to talk about them. Yeah.
So is this theoretical?
This is theoretical. This is theoretical physics. That is what we're doing. That's what it is. Okay, so so now I want to explain how you use this wormhole to accomplish quantum teleportation. So for that, I'm going to draw. This is even more risky. I'm going to draw for you the actual kinds of space-time diagrams that professional physicists use to describe these kinds of black holes. What we're going to do is we're going to take this situation with these two black holes here. To simplify the geometry a little bit, I'm going to imagine that there's no spatial connection here. The only spatial connection is through the wormhole. What that geometry looks like is the following. Okay, so this is a geometry that drawing that people currently at the Aspen Center for Physics make many times a day, although not normally on a in exactly this setting, so not quite as well. Okay, so this is a picture of the space-time of a black hole with two observers. So of these two black holes, so I'm drawing, this is a picture of space. This is a picture of space-time. So time goes up here and space goes sideways. And what have we drawn? So what have we drawn? So look at this line here. This line represents is some position each point in time. What this is it's the trajectory through space-time of an observer. There's somebody over here, let's say Bob. This is Bob. This is Bob at an early time. This is Bob at a later time. Bob at a later time. Later time. Later time. Later time. If you look at this trajectory, what you see is that it's kind of curving to the right. Curving to the right. That means is that Bob is he's accelerating. Bob has a rocket ship attached to him. He's trying to accelerate this way. That's why his line, instead of just, let's say, staying at a given point or moving on a straight line like this, that's why his line here is curving to the right. Okay, so that's one part of the diagram we've explained. That's Bob. Over here is Alice. And Alice is curving to the left. She is also on a rocket ship, and her engines are firing the opposite. So Alice is over here, Bob is over here. They're accelerating away from each other. So those are those two lines. Okay, what are the other lines? These squiggly lines, this squiggly line up here, this is the singularity inside the black hole. So this region here is the region inside the black hole. This is the space-time region inside the black hole. This region is also inside. And this squiggly line here is the future singularity of the black hole. What that means, this is the region inside a black hole where space-time ends. Anybody who falls into the black hole will be destroyed at this point.
That's the horizon then.
Oh, that's not the horizon. That's the singularity. So the horizon, let's discuss the horizon. What is the horizon? Well, there are actually two horizons. From Bob's perspective, this is the horizon. What that means is if you cross this point, you cross this line, you are doomed to hit the singularity. So the following rule describes these diagrams. The rule is that light rays travel at 45 degrees. So something that moves slower than light would be this kind of trajectory or this kind of trajectory. So these ones are okay. This kind of trajectory would be moving faster than light, and that is not allowed. Any trajectory on this diagram has to move inside 45-degree angle. Well, suppose we had somebody over here. They're confined to move within 45 degrees. So in their future, they're definitely going to hit the singularity. And the dividing line between people who are definitely going to hit the singularity and people who may not is this line here. That's the horizon. It itself is a light ray. That was 45 degrees. That's the horizon. And that's the horizon that Bob is trying his best to stay outside of. He's accelerating just enough so he's not going to fall into the black hole. He stopped accelerating, started moving on a straight line, he would cross the horizon and hit the singularity. He's firing his rocket ship, just barely hovering outside his black hole. Alice is doing the same thing. She has a different horizon, this one over here. So what this whole space-time actually describes, it describes two black holes. Alice is outside one black hole, firing her rocket engines, trying to move this way. Bob is outside his black hole, firing his rocket engines, trying to move that way. And so these are two black holes, like we drew here. Black holes. Alice is over here outside this one, and Bob is over here outside that one. And the geometrical connection, the wormhole that connects them, is just the fact that space connects these two. They're actually quite close together. Alice and Bob, their point of closest approach here, are actually quite close together on the two sides of the horizon. So this is an honest space-time drawing of two entangled black holes.
Theoretically, could those entangled black holes be on opposite sides of the universe?
Yeah, yes. That's a kind of important point. These two black holes, the distance between them here could be extremely large. But the distance between them, if they're in this particular entangled state, the distance between them through the wormhole would be short. So Alice and Bob could be outside what they think are two black holes, incredibly far away from each other. Incredibly far away from each other. If those two black holes happen to be in this particular entangled state, then Alice and Bob are actually close together. They're close together through the wormhole. That's this direction here. They're close together, even though the black holes might be, sides of the black holes might be very far apart.
So information could travel through the wormhole faster than the speed of light.
Okay, good. Let's see. Let's discuss information traveling through the wormhole. So far I've discussed the resource that we're supposed to try to use to do quantum teleportation. Resource is this space-time. Okay, so now let's try to do quantum teleportation. The setup for that is to imagine that Alice has a quantum state that she wants to send to Bob. So Alice has a quantum state. Use this notation to describe quantum states. She's carrying it with her along on her rocket ship, and she knows about quantum teleportation. She knows that black holes are supposed to represent, entangled black holes are supposed to be some kind of resource you can use to do quantum teleportation. So what does she do? Makes the obvious guess. I want to send this quantum state to Bob. I'm just going to throw it into the black hole. Bob is right over there. I'm just going to throw it. Just throw it and hope he gets it. And so what she does, she throws it as fast as it can go, which is the speed of light. So it travels on a 45-degree line. I have to draw this kind of carefully. Here's the trajectory of the quantum state. Takes it and she throws it into the black hole. And okay, does it make it to Bob? Does Bob receive the quantum state? No, he does not. Does not receive the quantum state. This failed. Alice just took her precious quantum state and she threw it into a black hole. Bad idea. The quantum state ends up at the singularity at the end of space-time. Okay, so that did not work. And the fact that that did not work is a very important property of quantum entanglement, which is that quantum entanglement by itself cannot be used to send signals. So if you and I share an entangled state, I can't just kind of do something to my copy and have you receive the message. Entanglement by itself does not allow signaling. It's kind of a non-trivial property of mechanics and of entanglement. And that is represented here by a geometrical fact about the space-time. Represented by the fact that, this 45-degree line stays behind that 45-degree line, and it doesn't make it out to the other side. So we're seeing here already a hint that some kind of detailed property of quantum systems and of quantum mechanics, you can't send messages with entanglement alone. That is being represented here by space-time, by some property of the space-time geometry. So that's, well, Alice isn't too happy about that because of what happened, but for our purposes, this is already interesting. Now let's try to do something better. So I don't know how well you remember the quantum teleportation protocol we started out with, but Alice, what did she do? She took her quantum state and threw it into a machine, and it did some measurement. She got this answer 3. So she did some kind of a measurement on the system, got the answer 3. So you should try that here. So she starts the same way, throws the quantum state into the black hole. A little while later, she does a measurement. She does a measurement here. What she does, just measures a piece of Hawking radiation. If you don't know what Hawking radiation is, that's okay. It's just a little bit of radiation coming out of the black hole. She has a detector where she's able to capture one piece of Hawking radiation, measure it. She measures it at this later time. And what that measurement does, measurements in quantum mechanics are a somewhat violent process. And what it does is it creates a little bit of positive energy that propagates into the black hole. She's now thrown 2 things into the black hole. That seemed to help very much. She threw her quantum state in, and she measured a piece of Hawking radiation later. They threw in a little bit of positive energy. Okay, that's what's happened so far. The final step in quantum teleportation is that Alice needs to tell the answer of her measurement to Bob. So she needs to say the number 3 over the phone to Bob. So let's assume Bob at this time knows that the answer to the measurement was, let's say, 3. So Alice measured some piece of Hawking quantum. She got an answer, tells it to Bob. Bob now knows the answer was, he doesn't have the quantum state. He knows the result of the measurement on this piece of Hawking radiation. What does Bob do? He acts with a simple operation on his black hole that depends on the number 3. He can act with a simple operation that depends on the result of Alice's measurement. And what that can do is it can send in the black hole a little small amount of negative energy. The reason that this is possible is that normally you can't easily create negative energy. But Alice and Bob are working together here. So Alice measures something over here. She creates some positive energy. She kind of makes a mess by doing a measurement. Bob can use the knowledge of the outcome of that measurement to clean up a vacuum fluctuation which would have existed over here, contributing positive energy. You can clean that up, remove it, and you're left with negative energy. I don't know if that makes sense. Don't worry about it too much if it doesn't. Point is that Bob can use the result of Alice's measurement to create a small amount of negative energy falling to the black hole. Yeah.
How does the Alice communicate the number 3 to Bob in the diagram?
Okay, good. So how do they do that? Well, yeah, cell phone. So exactly. So Alice has a phone. She calls Bob. So let's assume that the black holes are not extremely far away from each other, and Alice can communicate the result to Bob. That's one answer. That's one way that this protocol could actually be carried out. Okay. The point is that there are multiple connections. Let me leave it at that. I can answer more later. Okay, we're almost done. So we're completely done. We observe the following thing. There's a famous effect in general relativity, follows from Einstein's equations, which is called the Shapiro time delay. What it says is that if you send a light ray through a region with matter in it, the light ray will be delayed in its trajectory. So I shoot a laser in some direction to a friend somewhere far away. It will receive that laser light a little bit later if there's matter in the way. Not because the light gets blocked, but because the space-time gets a little bit curved by the matter, and that curvature delays the propagation of light ray. This is called the Shapiro time delay. Positive matter density curves the space-time a little bit in such a way that light rays are delayed in propagation. What happened here? Bob threw in a little bit of negative energy. Negative energy works the opposite way in Shapiro time delay. It becomes a Shapiro time advance. If I'm shooting a laser somewhere, you could somehow arrange to have some negative energy situated between me and you. The laser light would get there a little bit faster than it would have without the matter in between. So we can illustrate that in this diagram by saying that what happens is the new trajectory of this quantum particle has a time advance. And the trajectory with the time advance looks like this. As it crosses this negative energy, it looks like it goes backwards in time a little bit, so it goes back downwards, or downwards is backwards in time. So the trajectory of the light, or of the quantum state that Alice sent in, is now this one. And well, what happens? Bob receives it. So Bob receives the quantum state on his side of the black hole. So this operation of Alice making a measurement here, communicating the result to Bob, and Bob doing an operation, is able to make it possible to traverse this wormhole. Makes it a traversable wormhole. And that is space-time's way of accomplishing quantum teleportation. Quantum teleportation is this purely quantum mechanical thing discovered in the 90s by people who studied quantum computation, quantum information theory. And here are a pair of entangled black holes carrying out that protocol using the rules of space-time. You don't really even need to know quantum mechanics. You just need to know the rules of space-time to understand the implementation of quantum teleportation by black holes. Okay, there's a question there, but I just want to finish now, and then I'm happy to answer other questions. So thanks very much.
If Bob threw in any other number other than 3, how would the result of that the direction of the
Right. So if Bob doesn't know the outcome here, he just picks some other thing, then he's not able to send negative energy. Not able to send negative energy. It's like he doesn't know what vacuum fluctuation exists, so he's not able to kind of remove it. So if he doesn't know, then he's not able to send negative energy, and this protocol doesn't work. So in fact, without the communication between Alice and Bob, there's absolutely nothing Bob can do to send negative energy into the black hole. It's absolutely essential for them to have this information in order to do that.
Yeah, okay, so that
Yeah, maybe.
maybe in comfort.
I think I understand everything you're saying, but I'm a lawyer, so I'm not my thing, but what is what does this tell us in lay terms? What, I get it all.
Okay.
What is it?
Okay, good. So 2 answers. First is what this tells us is it's an example of connection, but of this absurd equivalence that I showed. This absurd equivalence between interacting system of particles and space-time theories involving black holes. And this is just one way of understanding an example of that. So if that is true, anything quantum mechanical systems can do, black holes ought to be able to do. And so here we're seeing an example, quantum teleportation. That is something quantum mechanical systems can do. It's kind of non-trivial. Here we're showing you how the black hole does it. That's one answer. Second answer is that often when you try to ask a black hole to do a thing a quantum mechanical system does, it does it in a way that surprises you. It does it in a kind of some insight to the problem. So the fact that the message goes through the wormhole adds a layer of understanding to quantum teleportation that did not previously exist. So there are 2 applications of that. So we had 2 answers to the question. Now, the second answer has 2 parts. So the first application of that is consider the following kind of crazy philosophical idea. What does it feel like to be teleported?
Star Trek.
Okay, but well, did they know that they were talking about the right answer? So what does it actually mean if somebody does quantum teleportation to you? And the normal quantum teleportation protocol doesn't really answer that question. Here we can answer the question. The question because we can follow the trajectory of the quantum state. And what it feels like in space-time, it just feels like inertial motion. It's like it's falling. Particle just feels like it's falling in essentially empty space-time from one side to the other. Okay, so it gives you more insight into the experience of being teleported in a more practical sense. So people have used this quantum teleportation protocol to design experiments that have actually been carried out on sort of noisy current quantum computers. This is an interesting quantum mechanical effect that the black hole told us about. The black hole picture helps us to understand that experimentalists can go back and try to understand better in an ordinary quantum system like a quantum computer. So it's an example of this kind of like ping pong ball bouncing back and forth between quantum systems and space-time, where every time it goes back and forth, both players understand the game a little bit better. That's my answer.
Okay, then in the second row.
I'm wondering if you have perhaps any friends in condensed matter physics that might have shared with you what more, if anything, we know about the state of matter inside a black hole.
Oh, well, depends where you are inside the black hole. Let's look at this picture here. Here we have a picture of space-time of a black hole, and this whole shaded region is inside the black hole. This is inside the black hole, and here, sort of barely inside the black hole. If it's a big enough black hole, things are basically the same. So you might not even notice that you're inside a black hole. Right?
Yeah, ordinary particles.
Ordinary particles, same rules of physics. If you could do an experiment, if it's a big enough black hole, you could design any experiment. You could do here, you could do it there, get exactly the same result. That changes as you get closer to the singularity. The singularity, space-time ends, and as you get close to the singularity, our currently understood rules of physics break down. We don't know exactly what happens there. Can't answer your question. And at the current moment, nobody can answer your question. At this point, everything looks normal.
But at that point, you're not getting that anymore. You're experimenting there, but your answer isn't getting back to us. Because
Right. Yeah. So you might know the result, but you can't tell it. Can't tell anybody on the outside. Though that can be subtle because look at this diagram. This red line entered into this shaded region. They thought, well, they was a state, but if they'd been a person, they would have thought at this point, oh no, Like I know about the space-time geometry, I have my like space-time map with me or whatever. I know that I'm behind the horizon of a black hole, I'm going to hit the singularity. But Bob can use this information to send in some negative energy and rescue them. So it's not always it's kind of an exception to the rule that you always hit the singularity across the horizon. You can in some cases be rescued.
So Hawking radiation emitted from something close to the event horizon?
Yes.
So Hawking radiation is the appearance of a virtual particle outside the event horizon?
Oh, it's the appearance of a real particle outside. So that
Well, that happens at the borderline that you're talking.
yeah, it happens here. So there's vacuum fluctuations here, and they propagate this way. And this one comes out and becomes a real particle, and this one falls in, hits the singularity. That's the process of Hawking radiation.
Back? Yeah. Two questions. Are you saying that what Alice did to perturb the energy and what Bob did they have to be simultaneous, or did they affect that in forever?
Good question. They have to be close in time, but not exactly simultaneous.
Okay.
Because the information that Alice gets by doing this measurement here, it's kind of only useful for a little while over here. It tells you about the vacuum fluctuations that exist only for a little while.
So she has to get the wave function in there quickly too, otherwise she'll miss that window.
Yeah, she needs to tell Bob the answer pretty soon. It doesn't have to be simultaneous. So if we had two black holes in the same universe, we could do a measurement and then tell Bob a little later. Maybe a lot later, but a little later, and it would work.
Could you just take a stab at explaining to us what the absurdity of that equivalence implies?
Oh, yeah. So, well, what it probably implies is that this is not known, but this is a reasonable guess. Is that what it implies is that fundamental description of you and me and our world and stars and galaxies and so on, a fundamental description of that might be an ordinary quantum system without any gravity in a lower space-time dimension. So we and our experience in all of this, gravity and cosmology, might really be kind of a another description of an ordinary quantum system. And that, I don't know, that's a the more you think about it, sometimes do think about that just in my daily life, not for like research reasons, but just it's a really weird thing to think about. So that's one thing that it might imply about our world. But on a more practical level, what it implies is that it gives you a whole set of tools that you can try to use to solve different problems. Like suppose somebody's trying to solve some hard problem, the theory of interacting particles that they can't solve because that's actually an incredibly hard problem. Quantum system of many interacting particles is an incredibly hard problem. And they can't solve the problem, let's say. What you could do if you know that a system or system like that one is secretly described by a black hole, you do some easy calculations in the black hole, and you say, okay, I think this is the kind of answer that you should get. And you know that actually has happened. That process has happened and has led to a new understanding of ordinary quantum mechanical phenomena. It goes the other way too. So there are phenomena in quantum gravity that we might not understand very well. And somebody could say, well, if your quantum gravity system is actually secretly just a description of a whole bunch of interacting particles, then it has to have the property of, for example, unitarity of time, some abstract property that all such systems have. So you know that then your quantum gravity system must have that property, and then you spend like decades trying to understand how it has that property, and that has actually also happened. That thing happened.
I was actually, before a question I was trying to ask was linking up the Hoyle's steady state theory with the idea that you could have matter leaving the black hole and then adding this to that space itself, where you could have, or possibly could have, like very small, very finely tuned wormholes that would lead into states that would perhaps transport this particle, which could be responsible for loss of mass, not necessarily some of the loss of mass outside, unless those 6 bosons are being transmuted or turned into gravitational waves, because you're losing mass with those mergers.
Well, the version of this that has actually been helpful in thinking about black holes, which is so you mentioned black hole losing a bit of energy slowly over time, and that happens through the process of Hawking ring. Black hole gets a little bit slower over time; it's emitting particle, and helpful way to think about that is to think about black hole as emitting small black holes instead of Hawking particles, small black holes that are connected by wormholes to the original black hole.
Black hole.
No.
Exactly, but
Like tiny black hole, highly quantum black holes connected by some wormhole to the black hole, the original black hole they started out with. That picture is, I believe that's a picture that actually helped Jeff Pennington, who's a physicist who's visiting here, to understand better the evaporation of holes and the important work from a couple of years ago that Henry Maxfield, who's actually here in the audience, simultaneously with that. So that picture of radiation as thought of geometrically as being made out of wormholes, though it's not a very efficient or economical picture, has been helpful for people thinking about that.
feel like quark sized.
Yeah, right. So fundamental particle size black hole. So it's not really a good description of that particle. It's not in detail correct, but it helped people to figure out the right answer for.
But quarks do have dimension, otherwise they would be black holes, because I mean, even though the gravity would be incredibly small, a true point in the Euclidean.
Right. These particles aren't really point.
So because we went over time, I think maybe this is the point where we stop the official part of the lecture. If there's urgent questions, I think there's some time possibly to ask afterwards. But let's thank Rob.
Okay. Actually, I have to go right now. But Henry is here, and he will answer your questions. So.
Random guy.